welcome to Analog Output. Let's take a look at one of the very simplest synthesizer modules you can build. You start with a diode, you take another diode, you connect it head to tail with the first one, connect a third diode, and you connect a fourth diode, and now you've got a ring of diodes. Okay, it's a square ring, but okay, it's topologically a ring. Work with me here. We have our ring of diodes. We're going to add to that a transformer on one side, and we're going to add a transformer on the other side. Okay, now we're going to make some connections. We're going to connect the top and bottom corners of the ring. Yes, the ring has corners. Shut up. We're going to connect the top and bottom corners of the ring to one of the transformers. We're going to connect the left and right corners to the other transformer. We're going to connect an input jack to the other side of one of the transformers. We're going to call that the signal input. We're going to connect an output jack to the other side of the other transformer. We're going to call that the output. And we're going to connect another input jack to the remaining terminals of the transformers. We're going to call that the carrier input. And that's the module. That's everything. And you say, wait a second, hold on, where do I connect the power supply? And the answer is, you don't. You don't need a power supply. All you need to do is connect, for instance, an oscillator to the signal input, connect another oscillator to the carrier input, and you get something on the output. And what you get is kind of weird. It's kind of got the shape of the signal input, but that shape has been chopped up by the carrier input, and every place the carrier is low, the signal gets inverted in the output. So what does this sound like? Well, it sounds kind of complicated and interesting. If you take a look at the frequency content of the output, what you find is that none of the frequencies present in the original signal or carrier are present in the output. Instead, what's in the output is sums and differences of the signal and carrier frequencies. And that adds up to a complicated set of frequencies, leading to a complex and interesting sound. So that is the ring modulator, with ring there referring to that ring of diodes you keep complaining about. I called this a synthesizer module, but the ring modulator was in fact invented in the mid-1930s, long before synthesizers. It was originally used in telephone systems, as I understand it, for multiplexing telephone calls onto a single wire. And it wasn't until later that evidently somebody said, let's put an audio signal on the signal and an audio signal on the carrier and listen to the output and see what it sounds like. Ooh, that sounds weird. That sounds wonderful. I want to make a synth module out of that. And people have been using them in synthesizers ever since. But there's problems with this design. In this case, it gives you the kind of output I've shown you here if everything's perfect, if the transformers are perfect, and if they match each other perfectly, and if the diodes are perfect, and they match each other perfectly, and the forward voltage on the diodes is 0 volts, and if the carrier amplitude is way larger than the signal amplitude, then you get this kind of nice output that we've got here. In the case where you're using real-world components, imperfect transformers, imperfect diodes, non-zero forward voltage, and carrier not that much bigger than the signal, then you end up with something that has various sorts of distortion in it. And in particular, you are likely to find that some of the signal and carrier frequencies do indeed bleed through into the output where they're not supposed to be. And then finally, to make the carrier input much larger than the signal amplitude, you either have to boost the carrier amplitude, which is probably not very feasible, or you have to attenuate the signal amplitude. And if you attenuate the signal amplitude, you attenuate the output, and you end up with a small amplitude output signal. So because of these problems, people have designed other circuits that don't use transformers and rings of diodes, but still do produce results that are kind of similar to the results that you would get with a ring modulator. And they sometimes refer to these circuits as balanced modulators or 4-quadrant amplifiers. Then again, sometimes they just brazenly refer to them as ring modulators, even though pedantically and prescriptionistly only something with a diode ring and transformers ought to be called a ring modulator. But they pass these other circuits off as ring modulators anyway. Not naming any names. But some people still like ring modulators. They've got a certain character to them. The more modern replacement circuits for them don't give you exactly the same kinds of outputs as ring modulators do. So some people still build plain old ring modulators. Ken Stone, who designs modules under the CGS name, has a design for what he calls the real ring modulator, which is, 2 transformers and 4 diodes. But Stone also has another design in which he takes the ring modulator core and he adds to it some powered active electronics to try to address some of the problems that you get with ring modulators. So on the signal side, he adds a second signal input. There's one that just goes directly into a gain stage, and there's another that first goes through a preamplifier. So you use the first of those if you want to use a synthesizer signal. Use the second one if you want some sort of external signal, like if you want to run a guitar through a ring modulator. You put it in this low-level input, and it goes through the preamp. So you've got some additional flexibility there. On the carrier input, well, again, there's 2 carrier inputs. This time there's one that's DC coupled, and there's one that's AC coupled to remove the DC offset. And then there's a knob that allows you to add a DC offset. So what you have is full control over the DC offsets. You can remove the DC offset, you can add a DC offset, you can change the DC offset, and any of that is going to generally change the character of the output you get. Then on the output side, there's yet another gain stage. In this case, it's amplifying the output of the transformer in order to restore some of the amplitude that you lost earlier on. But there's also a connection back to the signal input and a connection back to the carrier input. And there's trim pots there which allow you to adjust the amount of signal and the amount of carrier that you're adding in to the output of the ring modulator so that they just cancel out any bleed through that might have come through the ring modulator. So that eliminates, or at least it mitigates, the bleed through problem. You're still left with some distortion, but that's kind of part of the charm of the ring modulator, really. It gives it some of its flavor. So that's the Ken Stone active real ring modulator, and that's what I built, more or less. Of course, I always have to make some changes. The big thing I changed was I got rid of the low-level input and preamplifier, simply because I've got that on my envelope follower module, and I don't really need 2 preamplifiers going at the same time. There's a limit to the number of ukuleles I can play simultaneously, so if I want to put an external signal through the ring modulator, I'll just plug it into the envelope follower, take the preamp out from there, and put it into the one input on the ring modulator. I made not so much a change as a choice regarding the diodes. Stone says you can use any kind of diodes you want. He points out that you get generally more distortion with diodes that have a higher forward voltage. And germanium diodes tend to be what people traditionally use for ring modulators, partly because that was basically what was around in the early days, and partly because germanium diodes do have low forward voltages compared to regular junction silicon diodes. But on the other hand, Schottky diodes have generally even lower forward voltage than most germanium diodes, so Schottky would probably be a good choice for this too. But I decided to go old school and use germanium diodes. And then finally, I switched out the transformers. The ones Stone recommended are a little bit harder to acquire, and I decided to use a couple of different transformers that I was more easily able to obtain. They have a different footprint than the transformers that Stone specified, so I wasn't able to use the commercially available circuit board. I just designed my own circuit board and built the Kosmo format ring modulator. Let's take a look at it. Alright, so let's see what we have here. We have our signal input, which is a sine wave from one oscillator. We have our carrier, which is a little hard to tell because it's not synchronized, but it's a square wave from another oscillator. And then the output of the ring modulator is this thing here, which it's a little hard to see what's going on. If I just give you a single trace here, this is just what happens at one moment, and there now you can see this carrier is this square wave, and the output of the ring modulator is this thing here, which if you squint at it, it's like a sine wave, but it's chopped up and going back and forth and back and forth and back and forth. And then if you look at multiple triggers, then you can see it's got this sine wave overall shape to it. Now, one thing to notice here is on the module, the signal is set to a pretty low level. In fact, if you were to look at the level of the signal inside of the ring modulator, it would be something like plus and minus half a volt, as opposed to the usually more like plus and minus 5 volts that a synthesizer signal usually is. If I try to turn up that signal, what you can see is this becomes distorted. It's no longer the sine shape, it gets flattened out. And if I crank it up more and more, it just gets more and more distorted like that. So if we want to preserve that sine shape, we need to keep that signal pretty low. Alright, another thing is what happens if I turn the carrier down completely. Well, then the output just goes dead. There's nothing there if I turn the carrier down. What happens if I turn the signal down to nothing? Well, then there is something here. So this is carrier bleed through, and I've adjusted the trim pot in the circuit to try to minimize that carrier bleed through, but there is still some bleed through there. It doesn't go away completely. What's it sound like? Let's take a listen. I'll turn this up over here. Okay, and now if I vary the frequency of the sine wave, or if I vary the carrier frequency, okay, now here we have an ADSR in looping mode, and it's giving us a sharp attack and a long decay, and that's going into the VCA, and the result we get is kind of a bell-like sort of a sound. Okay, let's try looking at some different waveforms. This is the sine wave. If I change it to a triangle wave, here's a ramp wave. And a square wave. Back to the ramp. If I change the carrier waveform, that's a sine wave carrier. And now if I vary the carrier unbalance, that does different things. Let me try filling with this. So that gives you some tools. There you have it, the active real ring modulator by Ken Stone. Interesting module. There's certainly some issues, in particular the carrier bleed through. I sort of get the impression that Stone's design does mitigate some of the problems associated with the traditional ring modulator circuit, but doesn't eliminate all of them. You know, either that or I just made some mistake in my build, which is also always a possibility, I guess. Another thing I've been thinking about is the diodes. I referred before to wanting to have diodes with a low forward voltage, but I've been doing some LT Spice simulations recently, which have led me to wonder if that conventional wisdom that low forward voltage is better for ring modulators is necessarily fully correct. And I've got a blog post about that. There's a link in the description down there. Take a look at that. If you have any insights on that subject, I'd be happy to hear about them. Other than that, got more videos coming up. There's more modules I want to tell you about. So stay tuned and subscribe, and I'll see you next time on Analog Output.